In this video, we're going to look at a second AP problem that uses the concepts from section 10.1. As I read this, I'm going to underline important information that I might want to use later on. A French study was conducted in the 1990s to compare the effectiveness of using an instrument called a cardiopump with the effectiveness of using traditional cardiopulmonary resuscitation, CPR, in saving lives of heart attack victims. Heart attack patients in participating cities were treated with either a cardiopump or CPR depending on whether the individual's heart attack occurred on an even-numbered or an odd-numbered day of the month. Before the study, a coin was tossed to determine which treatment, a cardiopump or CPR, was given on the even-numbered days. The other treatment was given on the odd-numbered days. In total, 754 patients were treated with a cardiopump and 37 survived at least 1 year, while 746 patients were treated with CPR and 15 survived at least 1 year. So those are our two survival rates, or proportions of people who survived at least 1 year. Question A says the conditions for inferences are satisfied in the study. State the conditions and indicate how they are satisfied. So when you get an AP problem that specifically asks you about conditions, you need to be a little more detailed, because it says not just to list them and say, yeah, something was random. You need to say what was random and how it was random and so forth. So we're going to go through this first. So the conditions. Patients with heart attacks were randomly assigned treatments. Odd days and even days got different treatments. Okay, so there was a random selection about which group of days, odd days or even days, got different treatments. And I probably should even say a coin was tossed to see which treatment was on even days. So in this case, we have an experiment where patients are randomly assigned to two treatments, either the cardiopump or the CPR. Now the second condition that we usually check is the 10% condition, but you should not check the 10% condition because that only applies to random samples, and we do not have a random sample here. If you do something with the 10% condition on this problem, it would be wrong. Okay, third condition, we need to check whether or not we have a large enough sample that a normal model could be used to do the test. So we saw that we had 37 out of 754 who survived at least 1 year using the cardiopump. So that would be my proportion, then times the sample size, I just get 37. So basically NP is just 37, and it would be okay to just write NP is 37 and NQ is then 754 minus 37, which is 717, both of those greater than 10, and that's for the cardiopump. For the other one, the CPR, we had 746 times 15 over 746 is 15. That's greater than or equal to 10. That's my NQ. So I should probably put here NP. This is NP. And I labeled that for CPR. Now, you could also use a subscript, and that's what we're going to do from now on, actually, with the rest of the test. So the CPR, I'm going to say the proportion here is P sub CPR, and for the cardiopump I'm going to call that PCP. Now that's not really great. If you wanted to do that in hindsight, maybe it would have been better to have called P sub P is cardiopump and P sub C is CPR. However, we've got another P sub C later on in the problem, you'll see. So we could have also called them 1 and 2, P1 and P2, and just designated that cardiopump was 1 and CPR was 2. So there's lots of different ways to use subscripts. This is what I chose for this problem. Okay. Secondly, perform a statistical test to determine whether the survival rate for patients treated with a cardiopump is significantly higher than the survival rate for patients treated with CPR. When you see rate, survival rate, that indicates a proportion, because it's like 37 out of 754, whatever percent is, that would be our survival rate for the cardiopump. So let's take a look at the different pieces that we're going to have to do. So our state piece is that, first of all, I wanted to think through the problem. The question is the proportion of patients treated with the cardiopump and that survived 1 year after their heart attack greater than the proportion that was treated with CPR? Another way of saying that is the difference greater than 0 when we subtract it in this order? So I am going to define then my parameter of interest as the difference in population proportions of patients getting cardiopump or CPR who survive at least 1 year. And I notice I said population proportions. So the population being people, I should say the population proportions of heart attack patients, because that's who we're specifically dealing with, not just population proportions of people in general, but heart attack patients who survive at least 1 year. When you write out what it is that your parameter of interest is, it's often very wordy, but you do have to be very specific. And often the way it's worded in the question is a good guide for how you want to write that in your population parameter. Now, our null and alternate hypothesis. Basically, what we're looking at is for the null hypothesis is that there's no difference, that the proportions are the same whether they were treated with a cardiopump or a CPR. What we're trying to find out and find evidence for is that the cardiopump works better, so proportion of survival rate proportion for cardiopump is greater than CPR. But we have to have a number to work with. So we end up subtracting and saying the difference is equal to 0 or the difference is greater than 0. Now, what I'm going to do next is enter the thing into my calculator. So that would be actually the next thing in the procedure that I do. So I'm going to kind of scoot this over and show what's going on the calculator here. Here are the results I got, but let's go ahead and do this on the calculator, and we'll talk about, I guess I can drop this down. We'll talk about then how we're going to handle that. So if I go to the menu and statistics and stat tests and go to a 2-proportion z-test. This is a 2-proportion z-test. And my number of successes was 37 out of 754 for the cardiopump and 15 out of 746 for the CPR, and I want a greater than test where the first one is greater than the second one. And then here are my values I get. So we'll go back and now talk about what all of these numbers mean. Okay, so the first we have our z-score and our p-value, which of course are both very important, our test statistic and our p-value. But what do all these other numbers mean? Well, we have p-hat1. Well, that's our cardiopump. P-hat1 is 37 over 754, 0.049. I shortened it a bit. The sample proportion for CPR was 15 over 746, and that's the 0.020. Now we have this other p-hat, and this is called p-hat combined or p-hat pooled, and we're going to talk about where that comes from. That is the combined success rate over the combined sample size, and we have basically throw these two groups together into one big happy sample, and we have a proportion associated with that. Now, why do we do that? Well, the reason we do that is in a hypothesis test, we start with the assumption that the null hypothesis is true and then try to reject it. So if we assume that the null hypothesis is true and there's no difference in the survival rates for the cardiopump versus the CPR treatments, then if there is no difference, we can combine them together into one sample and just use the total number of survivors over the total sample size, and that's going to be our null hypothesis value that we're going to use to find standard deviation for our model in the statistics test. So p-hat combined or p-hat pooled is based on a no difference between proportions hypothesis. So we have the mean then of our model. The mean of the difference in sample proportions is just 0. But if we use 0 for our sample p-hat, our sample difference in proportions, then we wouldn't get any, we would have 0 for our standard deviation. We don't want a 0 standard deviation. So what we use for standard deviation is the p-hat combined or the p-hat pooled version. So notice we don't have the different proportions for each sample. We have the same proportions here for each sample size based on combining together the two samples. So this is what's known as the p-hat pooled, the p-hat combined. And this is where we get the sigma for our model. Now none of this particular value is not anywhere on the printout. But if we look at how z is calculated, if you take the difference between p-hat 1 and p-hat 2, which is about 0.29, and subtracting 0, which is our null hypothesis value, the standard error of the statistic, or the standard deviation of the statistic, is 0.00949. This is rounded, so it's not exactly 3.066. I think it turns out to be like 3.055. But if we didn't round these values, that's where z comes from. And of course, our p-value is the probability of getting a difference that is more than 3.066 standard deviations from the mean, which is obviously a very small probability, because that's 3 standard deviations from the mean is very unusual. So that's 0.001. At an alpha equals 5% level, or any alpha level for that matter, we can conclude that we have strong evidence to reject the null hypothesis. We can conclude that the true proportion of those who survive at least 1 year after a heart attack is greater if the patient, I shouldn't say it was, is treated, because we don't want to say, we don't want to refer to the sample, is treated with a cardiopump instead of CPR. So the big differences here are using this p-hat combined for finding the standard deviation of the model when we do a hypothesis test, not when we do a confidence interval, only for a hypothesis test. So where does this show up on the formula sheet? Okay, it shows up right below the special case here. So this is the one we would use p-hat 1 and p-hat 2 and q-hat 1 and q-hat 2 if we're dealing a confidence interval. So we'd use this one for a confidence interval. But when we hypothesize that p-hat 1 equals p-hat 2, if we assume, okay, if that's our assumption, assumed for the null hypothesis, then we use this version. We say they're the same, okay? We assume that the two population, actually we can't assume that the two samples are different. We're assuming the two population proportions are different, are the same, sorry. Then we can use the p-hat pooled. So what we do is this p here is equal to x1 plus x2 over n1 plus n2. That's where this p comes from. And then we call that the p-hat combined. So that's the p-hat combined. The p-hat combined would go both numerators, and then the two denominators are the two sample sizes. Now if I factored out the numerator, then it would look like this, and then if I split this into two separate radicals, it would look like this. So that is why we have a formula that looks like this on the formula sheet. P times 1 minus P times the standard deviation, or times the square root of 1 over n1 plus 1 over n2. So it's what I showed you before, but with different symbols and with a little bit of algebraic manipulation to make it look slightly different. I'm not really sure why they write it this way instead of writing it with the numbers on top, but I wanted to show you that it is the same thing I showed you on the notes. Just one more comment. Okay, that's the wrong one. Go back this way. Okay, one more comment is that page 620 to 622 does some really good job explaining this p-hat combined, and showing you an example problem. And then page 625 and 627 do a really good job of talking about how we write differently about a hypothesis test where the two proportions come from a randomized experiment versus a 2 randomly selected samples. So that would be really important also to read.